Hey you guys, welcome to the Statistics Fun Room. On this video today I want to look at like an introduction to some basic probability concepts. So usually when we define a probability, what we would talk about is we're looking at a specific event. Right? So in other words, probability I can't spell today. So if we're looking at the definition of a probability, we typically look at what we would call an event E, right? And so in other words, we would look at the number of outcomes favorable to our event. Let's say outcomes favorable to E over the total possible outcomes. Alright, so in other words, to put some numbers to this definition, let's do something really simple. Let's say we're looking at a six-sided die. So let's say we roll a six-sided die and we record the upside, let's say. Alright, so let's do a couple things here. Let's letter A, let's list all possible outcomes. Alright, so if we're rolling a six-sided die, we're assuming that the die is fairly weighted. No one particular side is going to occur more frequently. So what are the possible outcomes that we could observe here? So on a six-sided die, I could roll a 1, I could roll a 2, a 3, a 4, a 5, or a 6. So these are all possible outcomes for this probability experiment. Now, usually what you'll see within a textbook is this is called the sample space. So the sample space is typically defined as the list of all possible outcomes. That's what we would call our sample space. Now, let's say an event that we're going to consider. So let's say we're going to look at, let's say, what's the probability, and my grammar is not the best here just because I want to be a little quick and efficient. What's the probability that we roll, let's say, a 2? What's the probability we roll a 2? So if we look back up at our definition up here, right, we said the probability of an event is the total number of outcomes favorable to the event divided by all possible outcomes, right, the number of all possible outcomes. So if I'm looking at what's the probability that I roll a 2, right, what I'm looking at in this case is, let's say, E is the event that I roll a 2. So I'm looking at the probability of event E in this case as being the total number of outcomes, the number of outcomes favorable to this event over the total possible outcomes. So we can see in our sample space there's 6 possible outcomes, and that's our denominator. And then, how many ways are there to roll a 2? Well, there's only one way. I roll the 2. So there's 1 out of 6 as our probability for that particular event. So introducing a couple terms using an example here, right? What's the probability definition, right? The number of outcomes favorable to E over the total possible outcomes. Sometimes it is convenient for us to visualize, if you will, all the outcomes in the sample space. So what are all possible outcomes for a particular event? So let's do a couple other problems here, and we'll introduce some other terms as we do these problems. So let's say we want to find, and I'm going to get lazy here, let's say we want to find the probability of an even number. So for this particular example, right, what's the probability of rolling an even number? Right? So the probability of rolling an even number is going to be out of all 6 outcomes, how many ways are there for me to roll an even number? So again, if I come back up to my sample space, I can see there's a 2, a 4, and a 6 that satisfy the event of rolling an even number. So we would have 1, 2, 3 possible ways to do that, and if we reduce, that's 1/2. Okay, so again, here's 2 examples of looking at probabilities of specific events. Then let's discuss 2 other problems. So let me tack on to this. Let's say we're going to do letter C. We just did letter C. Let's say we're going to do letter D. And let's say for this one we want to find the probability of not A2. So in letter B, we found the probability of rolling a 2. Here we're going to look at the probability of not rolling a 2. There's two different ways that we can attack this. Let me see if I can scroll back up for a second. So in my sample space, right, how many things are not a 2? So obviously if one of them is a 2, then 1, 2, 3, 4, 5 of them are not a 2. So in this case, my sample space is pretty small, and I can count like we just did. We can say out of the 6 outcomes, 5 of them were not a 2. All right, now what I want to kind of attack here for a moment is what we call the complement rule. So I want to point out to you here, let me change colors again, that the probability of rolling A2, getting A2 let's say, plus the probability of not A2, what's that going to be? So the probability of getting A2 was 1 out of 6. The probability of not A2 was 5 out of 6, and that gives us a total of 1. Okay. So intuitively, right, what we're saying is there's one way to get a 2. All of the other outcomes in the sample space are not A2. So when I look at all the ways to get a 2, all the ways to not get a 2, that's all the outcomes in the sample space. And this is what we call the complement rule. So what we typically would do is say the probability of E plus the probability of not E is going to be all of the possible outcomes in the sample space divided by all the outcomes in the sample space. So we would always get 1 in that scenario. Now in some books you'll see them use what we call prime notation to represent the complement. Right? So that's just another shorter way to represent the complement rule. Now also in some textbooks you'll see them do this in a particular manipulated version, if you will. So algebraically, right, if I'm looking for the probability of E, I could take this term here and subtract it to the other side. So I could say the probability of E is 1 minus the probability of not E. Or we could say, so if I solve for this term, I could take this one and subtract to the other side, right? So I could say the probability of not E is 1 minus the probability of E. Okay? So these three formulas, if you will, are what we would call the complement rule. Okay? So let me say complement rule. All right? Now let's come back up to what we just did in letter D. See if I scroll back up for a second. And again, what we had done is actually counted, right? We said, well, we knew the probability of a 2. There was only one way out of 6 that could occur. And then what's the probability of not a 2? We literally looked in our sample space and counted all 5, right? What we could have done in this case of probability of not getting a 2, we could have said that the probability of not a 2 would be 1 minus the probability of getting a 2. Let me scroll back up so you can see that, right? So we would be looking at like not E, right? So the probability of not E would be 1 minus the probability of E. Now because we had already calculated the probability of a 2, then that was 1/6. Right? So the probability of not a 2 would be 1 minus the probability of a 2. So that'd be 1 minus 1/6. And then, I could get a common denominator here. Common denominator is 6. So the number 1. It's really 6 over 6, and then I get 5 over 6, which is what we got from counting earlier. Now, why would I want to use the complement rule? Well, what we'll see in later videos is sometimes it's a lot easier to count how many ways something can occur, but what we're looking for is the probability of it not occurring. So instead of trying to count all of these possibilities of not A2, we'll go ahead and count the probabilities of that occurrence and use the complement rule, 1 minus that. Now again, in this particular example, it wasn't really necessary because the number of ways of not getting a 2 is very easily countable. And in future videos, we'll see situations where the complement rule would be much, much more convenient. All right, so let's take a look at another example, and let's make this example a little more difficult than what we just looked at, where we were flipping a coin 6 times. So let's suppose in this experiment, right, let's consider that we roll a 6-sided die and then flip a coin. All right, so what I want to do is, a couple parts to this problem like we did in the last problem. So let's say part A, let's list all outcomes in the sample space. Oops, that's a funny looking M. So let's list all possible outcomes in the sample space. All right, now in this situation, it's a little bit more difficult, or I should just say a little lengthier. And it's not overly difficult, right? But we're going to talk about a particular technique that we call drawing a tree diagram. There's a couple different ways that you can do this. It usually depends on whatever book you're looking at in particular. Right? I like to do these horizontally. It tends to give me a little bit more space. So let's say that my first action is the rolling of the 6-sided die, right, which is what's described up here. So in this particular order, rolling the 6-sided die, I could get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. I'm going to put a little bit of space between those numbers because I'm going to squeeze some stuff in between them. Now, my second action is to flip a coin. So let me change colors here. So let's say I roll the 1. Then when I flip the coin, I could end up with a tail, or I could end up with a heads. And we usually don't draw an arrow. Let me fix that, right? We usually just draw like a line. So it's almost a branch. And we call this a tree diagram. And the reason why is we're thinking of this as a part of the tree, and then we have 2 branches that connect to other parts of the tree. So let's suppose I roll the 2, then I could flip a tail or a head. If I roll the 3, then my next action of flipping a coin could produce a tail or a head. And again, the 4, I roll the 4, I could then flip a tail or a head. I roll the 5, I could then flip a tail or a head. And I roll the 6, and I could then flip a tail or a head. So this is called the tree diagram. And the tree diagram is intended to help me see all the possible outcomes in the sample space. So I'm going to change colors again. I'm going to pick gray here. So if I follow along each branch, I could get a 1 and then a tail. So I could get a 1 and then a tail. Or I could get a 1 and a heads. I could get a 2 and a tail. Or I could get a 2 and a heads. And I'm going to repeat this by listing all the combinations. Now remember, we called this the sample space. So here's the list of all possible outcomes for my probability experiment. And now if we look at all these possible outcomes, how many do I have? Right? Well, I really have the 6 possible outcomes for the first. I have 2 possible outcomes for the second. Right? So I have 6 sides of the die. I have 2 sides of the coin. So this is called the counting principle. It's just to kind of connect to what we just did. We have 6 possible outcomes for the first action, 2 possible outcomes for the second action. That gives me 12 total outcomes. And we can see that that's exactly what we listed. Right? If we count all of the gray options here, I have 12. 12 possible outcomes for this experiment. So this is my sample space. We have 12 possible outcomes where we roll the die first and we roll the coin second. Now the advantage to this tree diagram here is that it keeps things nice and neatly organized for me. So if there's other questions that I ask, like we're about to do, then I can look back at that sample space that we have here, and I can count, what's favorable or what's not favorable. So for example, let's say we're asked to find what's the probability of getting let's say an even number and a tail. Right, so in this case, again, the advantage to the sample space is I can come back and I can count how many outcomes are favorable for this event, right? So again, we're saying that we're looking at the probability of, let's say, an even and a tail. So I'm going to look at, out of all the 12 possible outcomes, how many are favorable to this event. So I'm going to come back up here. I can see a 2 is even and then a tail. So there's one way. 4 is even and then a tail. So there's 2 ways. And then a 6 is even and a tail. So I have 3 possible outcomes favorable to my event. So 3/12 or 1/4, right, if I simplify that fraction. So as a decimal, that's 0.25 in that case. Right? So the visualization of the sample space helps me count how many outcomes are favorable to my event. Now again, just to connect to the complement rule, what if we say what's the probability of not an even and a tail? Okay, so again, this is a relatively small sample space. I could look back up and I could count, or I could remind myself of the complement rule that this is 1 minus the probability of getting an even and a tail. So I know that the even and a tail was we reduced to 1/4. So I have, 4/4 minus 1/4, which is 3/4. Now, obviously, in a decimal form, 1 minus a quarter, right, is 3/4, right? That's the 3/4. So there's a probability of not getting an even and a tail. All right, so a couple other examples I want to look at here, and then we'll end this video. I don't like for the videos to get too long, but let's introduce a couple more concepts here. So in the examples we looked at so far, we talked about flipping a coin or rolling a die. And what we have done is we've listed out the sample space for each of those probability experiments. Now, when we're able to list out the sample space, what we call that is a classical, or some books call it a theoretical probability. Again, what that means is that we can list, all right, this term basically says we can list all possible outcomes. Now, think about flipping the coin. So if we come back to the first example and we flip, or actually that wasn't our first example, was it? That we rolled a die. Let's consider flipping a coin, right? So let's suppose we're flipping a coin. So we know that in our sample space we get a tail or a head. That's all we get. Now, let's say that I told you to pause the video and take out a coin, quarter, penny, nickel, whatever, and let's say flip it 10 times. And when you flip it 10 times, you record, let's say, the tails that show up. So for fun, why don't you do that for me, right? Pause the video, take out a coin, flip the tail, and tell me how many tails you get from that flipping. Okay, now that you have unpaused the video, I would assume, and would probably be correct here, that all of you, or almost all of you, did not get half, right? 5 out of 10 flips. Now, theoretically, you should get 5 out of 10, right? There's a 1, chance to get a tail out of the 2 possible outcomes. So theoretically, we're calculating the probability of getting a tail as 1 out of the 2 total outcomes. What you notice in practice is that's not always the case when I flip a coin a small number of times. So this introduces the idea of 2 things. The first being experimental probability. And I want to come back and talk about why we got the result for the coin in just a second. So if we talk about, empirical probability, basically probability. I want to make sure I can spell correctly, right? So basically, empirical probability is talking about the probability of things that we can't list all of the possible outcomes for. Right, so in other words, I would have to collect data is what I would do. So this is based on observations. Now, if you think about an insurance company, like let's say automobile insurance. So in an automobile insurance situation, if you are a driver between the ages of 16 and 24, you have a much higher charge for your monthly or your annual interest, your insurance rate, which you have to pay for insurance on your automobile. And why is that the case? Well, because the empirical data shows that drivers in that age range tend to have more accidents and tend to get more tickets. So, if we're asking what's the probability that an 18 to 24-year-old gets into an accident, we can't flip a coin to observe how many possible times that would occur. So what an insurance company does is they look at prior data. Let's say they look at the past 10 years or the past 20 years. They try to access data through, let's say, a Department of Transportation. And they look at what's the frequency, right? How many times did an 18 to 24-year-old get into an accident? So an empirical probability is based on observations, right? This is collected data, basically. Right? And again, the reason we would do this is we don't have access to being able to list all the possible outcomes of whatever our probability experiment is. Now, lastly, this brings us to the idea of the law of large numbers. So before, we kind of write down what that concept is, let's take a look at a simulation. All right, if we take a look at this simulation, what I'm doing is flipping a coin in the simulation, and I'm telling the applet, or the simulator that's doing this experiment for me, that the probability is 50-50, right? So 0.5. And what I want to do first is let's flip the coin 10 times. So I'm going to flip toss, and we're going to see up here at the top, it's telling me how many heads and how many tails that I'm getting. And it's counting the number of heads. So in this case, notice that I got exactly 5 out of 10. Now, most likely we won't see that again. So if I flip the heads this time, we're getting 5 out of 10. What are you doing to me? That's not supposed to happen. All right. That's pretty funny. So in this case, notice, right, we only get, or I don't say we get more than 5 out of 10. We get 8 out of 10 heads that we observe. So each time I flip a coin 10 times, I'm not always going to see 5 out of 10. In fact, that's kind of rare for me to see 5 out of 10 in that type of scenario. So in this case, how many heads did we see? We saw 2 out of 10. And I want you to keep in mind with the simulation, this is random, right? It is literally using a random number generator to find the number of heads. So in one scenario, we got 5 out of 10. Second scenario, we got 5 out of 10. Third scenario, we got 8 out of 10 heads. Fourth scenario, we got 2 out of 10 heads. So I asked you to pause the video and count the number of tails when you flip 10 times. And most likely, many of you would get varying results here. Now, what the law of large numbers says is that this empirical finding here, right, this is an empirical probability we just observed through data collection, that the empirical probability will become the theoretical probability the larger the amount of flips are. So the more trials that we run, the empirical probability will become much closer to the theoretical. So let's just stick with this one here, right? So we have 2 out of 10 heads that we observed. Let's go ahead and flip 200 more times. So if I toss, it's going to go really quick. And you can see they're graphing the probability that we're collecting cumulatively. And we can see right here the probability that we're collecting cumulatively as well. So out of 210 flips, we got almost 50-50. We're pretty close. We can see our graph is almost 50-50. If I flip 200 more times, I'm going to end up with 410 flips, right? I should be getting closer and closer to 50-50 the more trials that I run through this experiment. I end up with close to 50. So again, flip another 200, flip another 200 times, flip another two. Probably after I have flipped 1,000 times, I'm going to be at like 0.499. I'm going to be really close to 50%. So the law of large numbers says, as an experiment is run multiple number of times, right? So let's say this. Let's say as an experiment is run increasingly many times, the empirical probability approaches the theoretical. The empirical probability, I'm going to get lazy, empirical prob approaches the theoretical or classical. Right? Okay, and this is where insurance companies can get away with using empirical data, right? So first of all, they can't calculate theoretical probabilities within an insurance scenario, so they have to use empirical data, right? They can't calculate theoretical, they have to use empirical. And conceptually, the more and larger the data set is, so they're not just looking at, 10 18 to 24-year-old drivers. They're not just looking at 100 drivers that are 18 to 24. They have really large data sets, thousands and thousands of drivers. So they're using the concept that the more and more I run this experiment, the empirical data is becoming close to the theoretical probability. Now, one last definition or term we want to look at, and then we're done with probability. And the last one being that the probability of any event has to be between the numbers 0 and 1. Excuse me. So if I'm writing probabilities as decimals, right, not as percentages, right? Keep in mind, flipping a coin is 1 out of 2. That's 0.5 as a decimal, which is 50% as a percentage. Right? When I looked at rolling a 2 on a 6-sided die, right, that was 1 out of 6. I could write that as a decimal. I could also write it as a percentage. So when we're thinking of decimals, the values of probabilities have to live between 0 and 1, between 0% and 100%. Now, from this restriction, right, from this concept that is pretty intuitive, we can never have probabilities that are negative, right? We can't have probabilities that are smaller than 0. Probabilities have to be greater than 0, or they could equal 0, right? I mean, for our 6-sided die, let's say I asked, what's the probability of rolling a 7? Well, there's no sides, right? There's 0 sides that have 7, so that probability would be 0. So I can have a probability equal to 0. Let's say in that die rolling example, I say, what's the probability I roll a number less than 7? Well, all 6 sides are less than 7. So we would say 6 out of 6 are less than 7, and that's 100%, right? That's a 1. So we can have probabilities that are equal to 0, we can have probabilities equal to 1, and then all other probabilities have to live within that range of 0 to 1. All right, so that is everything that I wanted to discuss about like an introduction to probability. Look forward to seeing you in our next video.